Hello. In this video, we are going to derive the pi conjugated system for cyclooctatetraene dianion. Now, the neutral cyclooctatetraene is non-planar, and to see the point group symmetry assignments for that and related molecules, please see the link in the upper right-hand corner. For this video, we are going to assume planarity, which is true for the dianion. As a way of sketching it, we are going to put the planar molecule in the xy plane. So that is going to be the plane of your computer screen. And then the z axis is going to be pointing perpendicular to that. And the pi conjugated system is going to consist of the pz orbitals for the carbon atoms that are perpendicular to the plane of the molecule. In the chem method, using the correspondence theorem, we first need to identify the symmetry equivalent points in the molecule. And here there are going to be 8 such symmetry equivalent points representing the locations of the carbon nuclei. And just to make the sketch more clear, we notice that the xy plane is the plane of the screen, and the z orbitals are perpendicular to it. Because that is difficult to represent in 2 dimensions, notice that we have drawn the pz orbital here. They look like they're in the same plane as the screen, but we are to interpret them as being perpendicular. This is much like the tipped up tabletop that was used by the Cubist artist. Here in table 1 are the coordinates that we assigned to these 8 symmetry equivalent points. We are free to select any coordinates that we like, so long as they maintain the symmetry. For the time being, since we're just working with the framework of the molecule in the xy plane, we do not assign any z coordinates yet. In the chem method, we don't need to worry about the characters for irreducible representations. We just need the basis functions. Now, the set of basis functions that I show here, I obtained from a website, and the link to that website will be down in the box below the video. But for your notice here, we have them summarized. The irreducible representation label, and the corresponding basis function. From the 8 symmetry equivalent points in our molecule, we effectively generate a reducible representation known as the permutation representation that we denote by this delta 8. And we can reduce it quite easily in that it's going to consist of the irreducible representations that are non-zero when we substitute in the coordinates into the basis functions. And by that reduction, we get that it can be broken down into A1G plus B1G plus E2G plus E1U plus E3U. And remembering that we count the E doubly degenerate representations twice, we see that we've broken it down into 8 irreducible representations by dimension. in the following tables, we're going to evaluate each of those basis functions, and for them to be included in the reducible representation, all that is necessary that at least one of these orbitals is going to have a non-zero basis. So here we see that all of the bases are equal to 1 for A1G, but all we needed to do was the first one, so we could, if we were in a hurry, have stopped at that point. Next, we evaluate the B1G basis function at the 8 symmetry equivalent points. Again, we see that, in fact, all of the points have a non-zero value. So long as even just one was non-zero, then we know that it would be included in the reducible permutation representation, delta 8. When we get to a doubly or triply degenerate representation, we only need to evaluate one of the basis functions to prove that it is included in the reducible representation. So here we just use the first basis function xy, and we see that while there are 4 points that are equal to 0, we also have 4 points that are not equal to 0. So therefore, this is included in the reducible representation. Similarly, for E1U, we just use one of the basis functions, the function x, and we see that we have non-zero values, so it is included in the reducible representation. Lastly, in Table 7, we evaluate the last of the included irreducible representations, E3U, just looking at one of the basis functions, and we see that we have at least one position that is not equal to 0, so this doubly degenerate representation is included in our reducible permutation representation. In the point group D8H, we notice that the z basis function corresponds to the A to U irreducible representation. We can generate our reducible representation for pi bonding by multiplying that z times our permutation representation, delta 8. And we saw in detail what delta 8 was equal to, and here we show the formal multiplication of those irreducible representations with each other. To actually carry out the details included in the chart here, we have the basis function. So essentially, to multiply two irreducible representations, we multiply their basis functions. Whatever the product basis function is, it corresponds to some particular irreducible representation. So that is the product of the multiplication of the two irreducible representations. To evaluate the coefficients for each orbital corresponding to each irreducible representation, we simply evaluate the basis function for that irreducible representation at each of the symmetry equivalent points where the pz orbitals are going to originate. Now we have to include the z coordinate, and because it is a planar molecule, we're giving each of the z coordinates for each point to be exactly the same, to be equal to 1. So for the case of the A to U combination, we see that each point has an evaluated basis of 1, so therefore each one is going to have a coefficient of 1. We make our linear combination of atomic orbitals to make the molecular orbitals. And in table 9, we do the same process for the B2U basis function to get those the appropriate coefficients. Notice that some of the coefficients are 1, some are minus 1, and some are equal to 0. So it is distinct from the A to U combination, which it has to be. Now, when we're trying to evaluate the coefficients, when we have a doubly or triply degenerate irreducible representation, we have to use both or all three of the partner basis functions to get the appropriate coefficients. So here in table 10, we're using the first basis function xz. Now in table 11, we have to evaluate the second basis function for E1g, the yz basis function, to generate the appropriate coefficients for this version of the molecular orbital. So notice in the Kim method that when we have degenerate pairs or triplets, we evaluate each one of those separately. In the projection operator method, we would generate one of them first, and then by a complicated procedure on that particular linear combination, we would generate any further linear combinations. And that is often a source of difficulty and tedium in the projection operator method, which is very easily circumvented using the Kim method. Here we have the equivalent generation of the coefficients for the first of the E3G basis functions. In table 13, we evaluate the second E3G basis function for that irreducible representation. The final irreducible representation for pi bonding is E2U, and here we evaluate the first of the basis functions x squared minus y squared quantity times z at each of the 8 symmetry equivalent points where we have those carbon pz orbitals that make up our pi bonding. And finally, in table 15, we have the second of the E2U basis functions, xyz, evaluated at those 8 particular points, and the basis column gives us the coefficient for each of those atomic orbitals in the molecular orbital. Here, effectively, we compile the results of tables 8 through 15, and anywhere where the coefficient is equal to 1, we just omit it as is customary. If the coefficient is 0, then we just ignore the orbital that it would multiply, because anything multiplied by 0 is equal to 0. And so notice here that we have 8 linear combinations that correspond to the pi bonding in this particular molecule, dianion. We've also gone to the effort of changing color when we go from a positive phase to a negative phase, because an important factor in predicting the energies of these orbitals is the number of nodes in the orbital. Notice that these molecular orbitals have not been normalized just to save the amount of clutter on the slides. Also notice that our second E2U molecular orbital originally had coefficients of 1/2 for each orbital. So since eventually we would normalize the molecular orbital anyway, we can essentially multiply through by the number 2 and get coefficients that are all equal to either +1 or -1. All the difference that makes is it makes it a cleaner to look at. So here we display the A2U molecular orbital, where all of the p orbitals are in phase with each other. Remember, we're to interpret those p orbitals as being perpendicular to the plane of the screen. So we would notice effectively that above the ring is all the blue phase, and below the ring is all the red phase. So we have a completely bonding interaction throughout. Here is the first of the E1G combinations. And notice that we have denoted the nodes by a green line. So therefore, E1G has exactly one node. Here is the partner, the second E1G orbital, and notice that it has one node as well. So if you do a calculation and you have degenerate pairs and you get a different number of nodes, that is a mistake. So if they're degenerate orbitals, they have the same energy, they will have the same number of nodes as well. Next, we have pictures of the two E2U combinations, and notice that each of those has two nodes. Next, we have the two different E3G molecular orbitals, and again, notice that each of these has three nodes. B2U is our eighth and final molecular orbital, the final linear combination. Notice that it has four nodes, denoted by the green lines. Finally, to sum everything up into one picture, here we have representations of the 8 molecular orbitals where we have the pi bonding. We put them in order of energy based upon the number of nodes. A2U has no nodes, so it is the lowest in energy. And then proceeding up to B2U, which has 4 nodes, so it is highest in energy. In between, we have the 3 doubly degenerate pairs, put it in order of the number of nodes. Finally, we would notice that we have 1 pi electron for each carbon pz orbital involved. So that would give us 8 electrons. But notice that would give us 4n electrons, which make our molecule anti-aromatic and therefore non-planar. If we were, however, to make the dianion, that would add 2 additional electrons. So that would give us 10. So for 4n plus 2, with n being equal to 2, we now have the magic number, Huckel magic number, to make an aromatic system. So you predict this is going to be particularly stable and planar. I thank you very much for your kind attention. Stay healthy, stay safe, and as always, have a good one.